Now, in this section we are going to discuss the output analysis, specifically the variance reduction technique, and thereafter we shall look at simulation software, because please remember the simulation that we have shown, they are very rudimentary, and that kind of simulation is not sufficient. For proper simulation, if you have to do, we have to have a software. Now, there are different kinds of software in the market. We are not going to discuss about all of them, just one software Arena that we are going to discuss a little bit, and something about that, particularly how a queuing network can actually be simulated, that we shall see also in that particular section. So, let us start with the variance reduction technique. You see, we have seen first of all the length of simulation run very much dependent on this particular value, that is the variance, right. So, now you see the method that we have, variance reduction, that is known as antithetic sampling. What is antithetic sampling? In antithetic sampling, we are basically introduce a negative correlation between pairs of observations in a simulation experiment for obtaining more statistically reliable answer. So, what is really we are doing? We are really putting a negative correlation between the set of random numbers. How it is possible to really put some other random numbers which are negatively correlated? Let us look at one example. How the negative correlation to introduce negative correlation in random numbers. You see, let us take suppose we require 5 random numbers, and we assume these 5 random numbers chosen are R1, R2, R3, R4, R5. Now, it so happened that these random numbers, suppose the 2 digit only, let us consider, R1 is equal to 0.12, R2 is 0.56, R3 0.33, R4 0.81, R5 0.25. So, arbitrarily some 5 numbers I have taken. Now, let us see what is their total: 8, 11, 12, 5, 17, 1, 2, 7, 10, 18, 20. Their total is 2.07. So, what is their average? Average will be 2.07 by 5, 27057 by 5. So, it will be 41.414. So, look here, we have taken 5 random numbers, their average is 0.414. Interestingly, this average is not 0.5, because if you take 5 random numbers or even more random numbers, ideally their average should be around 0.5. So, these random numbers are on the slightly lower side, right. So, suppose they are estimating something and suppose these at estimate is directly dependent on the random numbers, then the estimate will be slightly on the lower side, because see, suppose the estimate is directly proportional to the random number value. Now, since random number value is slightly on the lower side, estimate will be slightly on the lower side. Now, assume another set of 5 random numbers 1 minus R1, 1 minus R2, 1 minus R3, 1 minus R4 and 1 minus R5. What are these numbers? 0.88, 0.44, 0.67, 0.19 and 0.75. So, these are the 5 numbers. What, see, they are just complementary numbers to each of the 5 random numbers that we have chosen. What are they? They are another set of 5 random numbers. So, it is not required to really make the total, we can directly write what is their average. Their average will be 0.586. How do I know? Because the average of 2 should be 1, because their sum are all 1, all right. So, what is this average? So, you see these random number values are on the slightly higher side. Because above 0.5. So, they are on the higher side. So, estimate will be on the higher side. So, compare this. Suppose we do one set of experiment with these random numbers, another set of experiment with these random numbers, then these two values, the estimates at the first set and estimates at the second set, this is the first set and this is second set. The estimate in the first set and the estimate in the second set will be negatively correlated, right. So, this is how we can introduce negative correlation in random numbers, right. So, this point is very important. How can I introduce negative correlation in random numbers? So, let us go back. So, in antithetic sampling, negative correlation is introduced between pairs of observation in a simulation experiment for obtaining more statistically reliable answer. Why it works? So, while estimating the mean value of a random variable, instead of simulation run of length n, suppose we run 2 simulation runs of length n by 2 are considered with values of observations in the 2 runs as yi's and zi's, right. Then the unbiased estimate of the grand mean x bar would be y bar plus z bar by 2, and the variance of this grand mean x bar of the 2 replications will be sigma x bar square is sigma y bar square plus sigma z bar square is 2 star covariance y bar z bar by 4. So, look at these equations very carefully. What have we done? We had the original run of length of simulation n, say n is 100, and what was the estimate? The estimate was x bar. Instead of that particular experiment, we are now dividing the simulation into 2 sets of 50 each. One set the mean is y bar, another set the mean is z bar. So, what will be the estimate of grand mean? Obviously, average of the 2. So, that is why you wrote the grand mean estimate is x bar is y bar plus z bar by 2. And what about the estimate of the variance? If the original variance was sigma x bar square, then the variance of the grand mean will be sigma y bar square plus sigma z bar square plus 2 star covariance y bar z bar by 4. So, in this relation, look at this relation very carefully. If to really estimate the relation, it is very much dependent on the covariance of y and z. But if y and z are negatively correlated, then the covariance value will be negative, and therefore, this sigma x square estimate will become lower, right, because of negative covariance here. So, that is the essential idea of the variance reduction techniques. Let us see how what happens. So, estimating, that is what we are doing really. So, variance of the mean of n by 2 pairs of observation will be less than the variance of the mean of the one continuous run of n observation. So, with negative correlation between each of the n by 2 pairs of observations, covariance term will be negative, right, because why it is happening? Because we are running 2 sets of runs, each with n by 2, and if this negative correlation remains, again how this negative correlation is possible? Let us look at this example, that is I have already given. The negative correlated pairs of samples can be generated by performing 2 identical simulation runs, but with different sets of uniformly distributed random numbers. In the first set, we use R 1 R 2 to R n by 2, and in the second set we use 1 minus R 1, 1 minus R 2, 1 minus R 3, etc. Thus, if R 1 is greater than average value, the 1 minus R 1 will be less than the average value and vice versa, right. Then 2 sets of random numbers will be negatively correlated. Hence, corresponding outputs will also tend to be negatively correlated, and the variance of the grand mean will be suitably reduced. What is the advantage if the variance reduced? The variance reduced, then we require less length of simulation run to estimate the same value. That is the advantage. So, here is one more example. In another example, let us say, let us look at this particular thing. This is about the simulation of this is a pen. So, simulation of an MM1 cube. Simulation of an MM1 queuing system. Now, in any queuing system, there are two most important consideration. One is arrival rate, and there is service rate. Look here, if more people arrive, waiting time will go up or go down? More arrivals in a given situation, waiting time will goes up. So, if more people arrive, waiting time goes up. If service rate increases, waiting time goes down. It is very clear. If you have better service, waiting time will go down. So, what is the relationship between arrival rate to waiting time? You can put it a plus. More arrival time, more waiting time. Service rate you can put a minus. That is, more service time, less will be waiting time. So, if you compare the two, then look here, the arrival rate and service rate, they are reversely correlated. If more is the arrival rate, then service rate should be increased even more. If arrival rate is less, service rate could be less, but suppose the opposite happens, arrival rate increases, but service rate reduced, waiting time will increase even more. So, their effect on waiting time is exactly opposite. That is the point I wanted to make. Let us look here, the inter-arrival time and time spent in the system are negatively correlated. So, if more is the arrival time, if this is the opposite way it has written, inter-arrival time. So, if inter-arrival time is short, customers are in the queue and spent longer time. Also, service time and time spent are positively correlated. Quicker the service, less is the time spent. Already we have seen that. So, thus inter-arrival time and service time have opposite effects on the time a customer spends in the system. Thus, inter-arrival time and service time are correlated negatively, right. So, for variance reduction, the following may be adopted. What we can do? Suppose we generate one set of random numbers to generate inter-arrival times in first replication and service times in second replication, in the second run, whereas another set of random numbers to generate service time in the first replication and inter-arrival time in second replication. So, look here what happens. The same random numbers which are used for arrival time in the first run, they are used to generate service time. So, what happens? The two replications will there be having negative correlation, and if they are negatively correlated, then what will happen? The overall variance will go down. If the variance goes down, then what will be the advantage? Then we have either we go for less number of simulation run, or we will have better results, right. So, that is the thing, that either sigma will reduce, or we can with the same sigma we can run with less number of simulations. So, in order to, that is the essential idea of antithetic sampling, that they are helping us in reducing the variance in the simulations, right. So, with that let us look at a little bit on the verification and validation part of simulation models also. Both the verification and validation, they are essential requirements, right. Again we know that verification means the model should be built right, or in other words the specification model should be the first model that we have, the computational model that we have developed finally out of the conceptual model, they should be consistent. But on the other side, the validation basically focuses on whether the proper system is developed or not. Basically, the correlation is not with the in the specifications that is obtained, but with the real system. And if the decision makers of the system whether they are happy with the system that is developed. So, here is a particular comparison, that when we have the real system and we have a conceptual model, first we must do a conceptual validation, right. How? Really talk experts and let them see whether the model does what is required. So, the conceptual model including system components, interaction between components and input and data assumptions really should see whether is at par with the operational model, means whether the specs are at par or not, that is called model verification. And finally, that computer program or the operational model should be calibrated and validated with the real system. So, that is how the entire verification and validation system should work, particularly in the simulation framework. With that, let us go to our next thing, that is about the simulation language. And as I said, one particular simulation language that we shall see, and essentially today's world, one of the very important software is known as the ARENA simulation software. It is a discrete event simulation software and mainly use the flowchart modeling methodology. So, what is the advantage? That you really do not have to write any equations. Suppose you have a set of what you call a queuing network, where a set of queuing systems, they are after one after the other, and from one block the thing goes to the next block, and there is certain arrival and service patterns. Then using some predefined building blocks of the ARENA software, you can model that system, and after modeling you can put appropriate values and the distribution that you have chosen, you can actually simulate a lot of variations and really come up with very interesting results. Not only that, it also has a facility for carrying out replications, generating a number of replications using the software. And finally, ARENA translates the user actions into a simulation language called Simon, right. That Simon language usually that executes the model, right. And finally, the output of the simulation is an estimate of the system behavior. Essentially the ARENA software really works on a large number of predefined building blocks. So, what are those predefined building blocks? Let us see them. Here are some of these building blocks. The very first building block is called a create, right. The create actually models the arrivals where entities sequentially enter the model in a specified pattern, right. So, what happens in a create block? That in a create block you really specify that what are the entities, how many entities are entering, and these what is the distribution that is coming up, and things of that sort, and they will enter one after the other in a sequential pattern. The second building block is called a queue. The queue provides an waiting space for the entities whose movements are suspended based on the system status. Why are they suspended? Because if the system status is busy, that means that these units cannot go to the next unit. What are the next unit? Where service is being provided, then they wait in a queue, and that is the essentially called a queue or a waiting space. The third one is called a seize. So, models entities from previous queue block to enter the seize block and seize an idle resource. So, the way it is put that first it seizes, that means it actually captures a given resource. Here resource is a serving facility. So, there is a service facility, the units are waiting in the queue block, and from queue block it goes to the seize block, and it goes to the seize block, then it actually gets that particular resource. And after getting resource, then there should include a delay block. What delay block does? It models consumption of time of entities as they are allocated resources. So, after the seize block, then they goes to the delay block, where the consumption of time takes place. That means the time it spends in the resource. Obviously, this time will be generated by a statistical distribution. Next one is the release block. After the delay, then that particular service will be over, and these entities will now release the resources, because activity requiring resources are complete, means the service is over. And there is something like a count, that count should really look into the number of occurrences of some event, and that will be counted. Disposed provides a mechanism for modeling the departure of entities from the system. So, usual simple simulations, we have not specifically look at dispose, because moment the release takes place we assume dispose has taken place, but it may not be happening, right. So, there could be a specifically dispose requirements also. Then there is a command called group. It groups a set of entities having a particular set characteristics. Then there could be split. The split is for degrouping. So, like we have group, we also have split. So, from the group that splits or degroups the entities that had been grouped earlier before they are disposed. Then assign values to attributes and variables used in a model. What is branch? It directs entities to different sections of the model depending upon the true or false condition. So, supposing there are two alternate paths to be taken or two different sequences for two different conditions, then based on whether that condition is true or false, the entities take different paths. So, here is an example I have taken, the reference is also given. You can see in this particular situation, first of all an order is arriving. So, it is an order processing system arriving for processing, the arrival time of the order is recorded. So, at the very first a create is given, then count is given and assign, a resource is assigned, and then they are grouped and then count and then duplicate, the number of orders received is counted, then it joins a queue, right. An order waits in the order arrival queue until its turn to be processed. Then there is a scan and then find j, the assembly line with the fewest items in the queue is determined, then assign and then finally queue, scan and finally split. So, one stage is over, right. So, like this we carry out simulations. Stop here, in the next section we will take up continuous simulation. So, thank you very much.